few terms we need to know here. The first term is what we call activation energy. And so that, by definition, is the minimum amount of energy required for a reaction to actually happen. Think of it like the hill that needs to be climbed, and I'll get to that again. Okay, a transition state is the moment in time where the reactants actually have the minimum amount of energy they need in order for the reaction to take place. And next is what we call the activated complex. So the activated complex is that species that I discussed earlier that exists sort of at the instant where the bonds are being broken and made sort of at the same time. So let's look at a picture of this. So here we have molecule A2 colliding with B2. And they're approaching each other. We're going to assume it's a successful collision. This thing that exists where the A2 and the B2 are all one whole unstable complex, that is the activated complex. Okay, and then eventually that unstable activated complex will want to reach a more stable configuration, and the newly formed products we see there on the right hand of this reaction as 2 ABs. So I want to relate some of the terms that we just saw to something called a potential energy diagram, and I've hinted at it before. We saw a simple one earlier. Okay, so remember that reaction that we looked at the very beginning to demonstrate successful and unsuccessful reaction. So here on my y-axis, my vertical axis again, I've got potential energy. And so I'm going to start out with certain reactants. Okay, my reactants here, and then there's going to be a collision. And assuming that that collision actually is successful, then I'm going to produce these products over here. But in the meantime, there's this energy hump, okay, this energy hill that I need to overcome. And as discussed before, that's the activation energy. So in this particular reaction, it's like these reactants need to climb over this energy hill to form products. Okay, so my activated complex exists while bonds are being formed and broken at the same time, so that exists right here. This is also coincidentally what we call the transition state. So if I had this new, like if there were numbers attached to this graph, I could draw a line across here and actually get a value for the top point, the activated complex point, the transition state. But I could also trace this back here and figure out what the initial energy was of my reactants. And the difference between those 2 points would allow me to get a value for activation energy for this particular reaction. Okay, in the same way, I can look at this reaction and see that my reactants are starting with a certain amount of energy. It looks like my final products have a lower amount of energy than what I started with. And so the difference between the reactant energy and the product energy describes the enthalpy change for that reaction. Okay, let's get to more specifics about this. So take a minute to take a look at these two graphs. They're just different versions showing an exothermic reaction. And if you need to pause the graph to check it out in more detail, by all means do that. So I can tell that both of these are representing exothermic reactions because it looks to me like energy is being given away to the surroundings by the system. I start out with a certain amount of energy in my reactants, and my products have less energy than they did. That means that the system must have lost energy. It must have given away energy in the process of reacting. Okay, so essentially, the distance between my products and my reactants represents the delta H, or the enthalpy for that reaction. Okay, as discussed before, the activation energy is the difference between the energy of my reactants and the energy of my activated complex up here at the top of my energy hill. And sometimes we we call that EA. We symbolize that with EA. So conversely, we can look at an endothermic reaction. So an endothermic reaction, instead we're going to expect that our reactants are going to start with lower energy, and then through the course of the reaction, we're going to see that our system has gained energy. Energy was taken into the system or absorbed by the reaction, and that's also going to give us a delta H value. So if you were to input some values here, if we had these graphs written with numbers attached, then we'd be able to make those calculations. But you can see that the activation energy required for your typical endothermic reaction is quite a bit greater than what we saw for the exothermic reaction in the last slide. So endothermic reactions typically require some energy input, okay, like heating up, for instance, in order to have the reaction proceed. So that's the end of our video. I hope that you understood everything and you'll come to class tomorrow with some questions. Please note that I have attached on Google Classroom a handout version of this presentation so that if you need to watch the video again and maybe write some notes or some questions down, then you're welcome to do that and bring it to class tomorrow with some ideas for discussion. Thanks so much. Bye-bye.